Hello, everyone. Hope you're doing well. It's a new week, which means we get to move on from the review that we were doing from last week. Remember, last time we separated our lectures into three different talks. One talk was about sets, another talk was about functions, and a final talk was about countability. Notice that in each of those types of talks, we were focusing on proofs of a specific type. We were looking at direct proofs, contrapositive proofs, all of which had to deal with sets and functions as the things that we were playing around with. Now, those are the building blocks for us. Usually, we're not attempting to just say one set is equal to another set. Now, though sometimes that is exactly what we're trying to say. And when we do that, we have that as a kind of thing to fall back on. But usually these are lemmas for us. To say one set is another set is just a lemma for us to prove something about another type of object. And in this class, what those objects are going to be are the objects of the spaces that we are studying. In particular, in classical analysis, we want to be studying generic spaces that have a metric on them. We'll talk about a metric space today. We also are going to be talking about normed spaces, all these various types of spaces. Our objects are usually not sets or functions, but spaces and what we can do in interactions with those spaces. That's why our textbook is called Spaces, is that that's kind of our main object of study, what we want to be going through. Of course, with spaces come sets and functions, so it's good that we got that as a starting point. That is one of the ways that we can start channeling the power of these spaces is by getting specific sets and functions that work in specific ways. And we'll start going, excuse me, start going in this direction a little bit today. It's talking about what kinds of sets and functions we want to look like. Functions that are continuous, for example, are very interesting and important to us. And we have a lot of neat theorems that come along with functions being continuous. But before we do that, we need to tackle a type of proof that we haven't seen yet. We talked about briefly the definition of how a sequence converges. And we did this in the case of the real numbers, and it was like this. We say that a sequence of real numbers S sub n converges to a limit L if for all epsilon greater than 0, there exists a value n that is in the natural numbers such that whenever the value of little n is greater than n, the absolute value of S sub n minus L is less than epsilon. Let's make sure that we understand the pieces that are floating around here. First, the epsilon is a y value window. It's saying, I want my sequence values to be close to this fixed point. L is a fixed point where S sub n is a sequence. We're saying that past the specific cutoff points, that cutoff point being n, we can think of this as a cutoff point in our sequence. Anything past that cutoff point needs to be in epsilon close to L. So we're saying this is epsilon close. When I say epsilon, I mean like a small number, and that number could be a half, it could be 1 over a million. Eventually, I need to say for any amount of closeness that I require, there exists a cutoff point, so that past that cutoff point in the sequence is close enough. It never jumps out of that epsilon window ever again past that cutoff point. So that's what we mean for a sequence to converge. Now, in our textbook, if you've done the reading, you might notice that it actually does something a little bit different. It puts a little greater than or equal to here for n. Well, this is the same sort of proof. Maybe you've seen this before, the same type of definition. Why is there greater than or equal to rather than a greater than? Because we can choose our cutoff points here rather flexibly. Let's say that n works as a cutoff point. Well, then n plus 1 is going to work as well. So is n plus 2, because all of the values past that cutoff point are supposed to work. So if this definition works for n greater than n, well, then it would work if I said this is greater than or equal to n plus 1. Vice versa, if I had something working for something greater than or equal to n, well, then it would be for any n value greater than n minus 1. So these two definitions work back and forth very much the same way. You can also think I could have put a less than or equal to here for epsilon and gotten the same sort of definition. But I believe that the way that our textbook works with it is the way that we will work with it. We will say n is greater than or equal to a value of a cutoff point n, so that the absolute value of S sub n minus L is less than epsilon. We will use this definition and just be consistent with it, because that's what I believe that our textbook uses. Now, epsilon-delta proofs in terms of the real numbers are something that we need to practice, and we're going to see some practice like that in our homework. We want to make sure that we are very thorough as we go through and work with these, and we're going to need that because when we start going into metric spaces, we're going to lose some of the properties that we're very comfortable with in real numbers. Let me give an example. So real numbers have a property of total orderedness. It means that if you choose any two numbers, you can say that one is greater than another number, or one is less than the other number, or the two numbers are equal. Sometimes this is called the trilemma, which is that given any two numbers, you can always put one of three things between them. One is less than two, one is greater than two, or one is equal to two. So you can always have one of those two properties regardless of the two numbers that you're choosing. But we're going to be talking about metric spaces, some of which involve functions as their elements rather than just numbers. Well, think about how you could say this between f and g. Given two functions on the real numbers, f and g, could you say that one function is greater than or equal to another one? Yes, you absolutely could. You could say that if you had, for example, maybe f is the function that looks like this, and maybe g is a function that looks something along these lines. If as long as the values of the function f are always greater than or equal to the function's values of g at any given point x that you might plug in, then that seems like it's perfectly okay. And to be specific here, it's okay even if parts of our values of our function g end up becoming greater than other parts of our function on f. It's only in comparison to each individual x value that we want our values of f to be greater than or equal to g when we write something like this. We could also similarly say when f is less than or equal to g, and so on and so forth. The issue arises when you're looking at functions that look like this. Maybe you have a function that looks like something here, and then you have a function that looks like something over here. Now I have, well, how am I comparing these two functions? Is f greater than or equal to g, less than or equal to g, or equal? I don't think I could say any of those three properties. So there's a lack of orderedness on this space, total orderedness to be specific, because I can't say given any two functions that one is greater than the other. I could say that for numbers. There's always some sort of orderedness property like this when it comes to the real numbers, but I can't say this for the space of functions. I also can't say this for the complex numbers while we're thinking about it. You can't say one complex number like I is greater than, equal to, or less than 1, right? That sort of thing doesn't work. You might say, John, why don't you just graph these on a two-dimensional plane and then say one is equal to the other if they have the same distance from 0? Right, so for example, I would be 1 up on the imaginary axis and 1 would be 1 to the right on the real axis. Well, that wouldn't make sense either because then I'd be saying 1 equals I. And I don't think that's something that I want to try and implement in my space, is that these two are the same, because they certainly do not act the same whenever they interact with some of these other numbers. So I will have some spaces here that have these properties, some of the things that we want, but not everything. So knowing and being very comfortable with epsilon-delta proofs in terms of functions, in terms of complex numbers, this is going to be very important for us as we move forward. So we're going to want to know a lot about these sorts of definitions. Now, I'm going to be working with these definitions today in terms of Rn, instead of looking at them in terms of R. Here, S sub n, that's a sequence of real numbers, and they approach a real number. But in this class, or in this slide, we will go ahead and immediately generalize those types of principles to the space of Rn, of basically n-dimensional space, where we're going to talk about how those properties work together. And the reason that we're going to go ahead and immediately jump to that point is that that's how metric spaces are going to work for us. We'll see some connections there at the beginning of week 3. So when we start putting in some of these theorems that need epsilons and deltas, you'll see that my sequences are sequences of vectors, not just numbers here. But there's something that I haven't defined. A quick tangent before my tangent here. I hope you don't mind that I just kind of talk about math here. I think that's something that is missing in an online class and needs to be instituted, is a way for us to be able to talk about math in a way that's more cordial and informal rather than formal. And so these sorts of discussions that I go into every now and then, I hope you feel like you're in that little bit of classroom atmosphere. Like, oh yeah, this is how you go about and do this. It's almost like you're talking with me on an informal sense, because we use the term analysis, but what does it really mean? I think those sorts of conversations are really nice to have. It seems strange to define the name of any mathematical subdiscipline as something you would do in any subdiscipline of math. You are always being analytical. You're always being engaging in analyzing the types of objects that you are studying. In algebra, you analyze everything you do. In topology, you have so much analysis that you have to undergo. So where is this notion of analysis coming from? Mathematicians disagree on this point, but it seems like a good place that we can kind of agree on is that Descartes' notion of analytic geometry, which was something that he named, and this is kind of a bit of an ostentatious name because he's saying, oh, before this, our geometry didn't have the Cartesian plane. It was just out there in ether and the space, and it wasn't quite analytical enough for me. It wasn't quite fitting to my tastes. So leave it to these sorts of instructors to kind of say a little bit of like, oh yeah, the type of science that we have is a little bit more enlightened, if you will, than the ones that came before. But this notion of analytic geometry seems to be where this comes from. You're looking at a world in which there's an X and Y and potentially even more axes. You're looking at a world of Rn. But once you get this sort of fixed point plane where you can give coordinates to any vector or point that you might give, then you get to start thinking about, okay, what happens if I manipulate and work with those points? I can now talk about adding two vectors. I can now talk about lengths of these vectors. That's exactly what analytic geometry was all about, was standardizing these approaches to very common notions, just making sure that like we could write all of these real world principles into something that is completely abstract and analytical, something that refers to literally just 1, 2, rather than something that is 1 foot to the right and 2 feet up. All right, that's a different concept, but something that can translate immediately into this world of the abstract. So this is exactly where calculus was born, was onto this plane. And so now we can say that we are developing arguments based off of our Cartesian plane. We are analyzing well-known geometric objects with respect to how this Cartesian plane works. So that's kind of a little bit of where analysis might be named from. Again, mathematicians aren't quite going to agree with me here. If you ask this to another professor, they might say something completely different. So we can just leave it as like, this is maybe a little something to kind of get us going, because that's exactly what we're trying to do. We're trying to analyze geometric objects and do something more rigorous than just say, okay, here's a box, boom, here it is. And then let's figure out what we can do with this box. It's let's think about the lengths that take place inside of here. What could we do with these things? If we change parts of these dimensions, what happens to these other properties, right? You may have remembered from calculus about how you can take something that is a three-dimensional figure and change dimensions of it and think about the change of volume with respect to those changes in dimensions, do some related rates problems, or optimize certain things of what you're looking for, maybe the cost of materials in building a box, once you've translated those sorts of objects into a kind of Cartesian format. So at the end of the day, what we're doing with all of this is asking about local properties, global properties, and the connections between them. The former asks, local properties are, what is true about our object around a given point? Around a given point. So for example, we would say that a function is continuous at a point x if something holds to be true around that particular point x. There's a little delta and a little epsilon window, you may recall. We'll get to those definitions in a bit. Whereas the latter asks, what is true about an object as a whole? You may also be familiar with the definition of a continuous function. That's something about a function as a whole. It's actually a global property that comes from gluing a bunch of local properties together. That is kind of our notion of what a global property might look like. But we want to study both sides. We want to see whenever a local property is present enough in a structure to become something that is about the object as a whole, a global property with that. For example, the small continuous points making a continuous function. Turns out that we're going to be able to find, okay, do you need every point to be continuous for a function to be continuous on a given region? And we'll be able to specify a little bit more of what we need in order to show that those locals glue together to become global. You might be familiar with compactness, for example, and we'll be talking about all the different types of continuity that guarantee something stronger, even if you don't have all of the typical local nature of properties that you might need that you would typically expect to get to a global property. There's some neat little connections here that are helpful to be discussing, this, especially between these two notions of continuity and compactness, which we'll spend plenty of time with in this class. To do that, let's go ahead and standardize our definitions. In terms of vectors in Rm, and I'll use m here because I believe this is how the textbook writes it. They'll use Rm typically when writing this. Now, sometimes you'll see me write, and I'll write something like Rn, and might be writing that for one of two reasons. One, I'm just used to writing R to the n. This is my typical way of writing this, so you might just slip. I might just slip and write it like this. Or I might be trying to distinguish from the fact that R to the n does not have the same dimension as R to the m somewhere else. Anyway, the norm of a vector is going to be its distance from 0. Norm of a vector is defined to be the distance formula, which is the square root of x of 1 minus 0, quantity squared, plus so on and so forth, all the way to x of n minus 0, quantity squared. This is the dot product of the vector x to square root it. Remember that the way that you define a dot product between two vectors, x and y, is to take x1, y1, add it to x2, y2, and then add that all the way to x sub n, y sub n. You can know that I'll be using this type of notation a good bit. If I'm working with a vector x, then I will be thinking of the vector x, even if I'm not writing it as such as x1, x2, xn. Here, the subscript x's without the little hats over them, those are going to refer to the coordinates of the vector x. And similarly for the vector y, this time using y1 through yn for those, so that this formula makes sense in terms of that dot product. So now distance between two vectors can be thought of as just the norm of x minus y. You're taking x of 1 minus y sub 1 and then squaring it and then going all the way down through there. When m is equal to 1, that is when I'm in a one-dimensional space, this is the absolute value of x minus y. If I'm trying to find the distance between 3 and 5, then I'm going to be taking it between the absolute value of 3 minus 5. That's the distance between those 2 points. It's the absolute value of -2, which is 2. Distance is always non-negative, and it's not going to be a complex number. It is always going to be a real number based on these results. Now notice here, first of all, that I'm in the real number. So of course, these calculations give us real numbers, and we'll have to change them a little bit if we ever get into the complex plane, but we'll do that when we get there. Okay. So a picture that is always helpful for me, and I'm very much a picture person, maybe you'll see this about me, is that oftentimes when I try to explain or explicate what's going on in a very text-heavy section, I'll try and draw a picture to say this is what I'm visualizing going on with this particular mathematics. So for example, these distances I could imagine as distances on a triangle. Let's say that I'm given 3 points. We're visualizing these points as vectors here. This is a vector u, v, and w stuck somewhere on a xyz plane, or an xy plane, in this particular instance, because I'm drawing on paper. So here I have vectors u, v, and w to be working with, and I can calculate the distance between v, u, and w using these formulas. Now you might notice that a bit of our geometric intuition is useful for what we're about to see, is that there is a formula down here about the triangle inequality. Now that I've written this triangle, I can use one of my geometric intuitive principles to help me make sense of this. The triangle inequality says this: given one length of a triangle, I could say that the length of that triangle is less than or equal to the sum of the two other sides of that triangle. The length of any one side of a triangle is less than or equal to the sum of the other two sides. Well, John, why are you saying less than or equal to? Why aren't you saying it's just less than? Because isn't that true? The sum is less than the two other sides. The only exception here is that sometimes when looking at u, v, and w, we're looking at things that are collinear. These three vectors are all in a line with each other. In this case, the triangle inequality is going to give us an equality, because the distance between u and w is exactly the distance between u and v, as well as the distance between v and w added together. So that is a place in which there is equality. But you're right in that that's the only case that you get equality in the triangle inequality, is when these 3 points are collinear. Now that's something that is useful for us, so it's worth writing down. So this is whenever I have something like the triangle inequality, and I could be writing this up here with these words if I need to, but the triangle inequality, equality only holds if the vectors given by, in this case, this would be x, let's see, the vectors x and y, but we have to say some specifics about them. So why don't I say instead that I'm looking up here at this line because it's a little bit more geometrically intuitive for us. The equality only holds in this inequality if the vector v that's given here is in the line segment connecting vectors u and w. Otherwise, you get a strict inequality. So that's the kind of place where you have equality there, is when it's inside of that line segment. Of course, it could be equal to u, equal to w as well, and that would work just as well. The way that this triangle inequality is usually simplified is that they'll take values like w minus v and v minus u and make those their own vectors, x and y. Putting all of that together gives us our notion of the triangle inequality that we will sometimes see in a kind of an analysis on the real line course, which is the norms of x plus y is less or equal to the norm of x plus the norm of y. And that is our triangle inequality. Right. You can also think of this as kind of like a triangle here. You've got the vector x here, you've got the vector y, and you're looking at the x plus y as taking the tail end of the first vector and connecting it to the head end of the second vector. And that gives us x plus y. And you can see the triangle using this picture as well, if that ends up being useful. So this way, we're focusing on x and y as the actual sides of the triangle here, rather than just the individual points. However, both of these formulas are very useful, and both are equivalently the triangle inequality. Something you'll notice about this one is that the first inequality we have, the norm of w minus u, introduces a third vector as something in the middle. It's almost like I'm subtracting and adding the vector v when I'm putting this in here. So kind of what's going on, the intermediate step, is that I'm saying that the norm w minus u is equal to the norm of w minus v plus v minus u. And now I'm thinking of grouping these things together and breaking them apart using the official triangle inequality given down here. And that's exactly where that other inequality comes from. The notion of distance is so central to what we're doing in this class in particular that we could remove the very notion of norm from our space. Now, this one's a little bit tricky. Like, think about what this is. Like, removing the notion of norm. That is the fact that these things have some sort of quote unquote distance from zero. Well, what if you live in a space where there is no zero? What if you live in a space where it's harder to determine things like distance from a given point and call that something like norm? Well, we can actually remove the notion of a norm from our space and still be left with something worthy of study. We will see that we are going to take space x and define a metric function on it that's going to take 2 points and spit out a real number, in fact, a non-negative number. And as long as that metric function satisfies many of the things of a norm, for example, if it satisfies the triangle inequality, and say that that space is called a metric space. Now, this is removing a lot of our typical ways of thinking about these objects, is that they do not have to have the order properties like we were talking about from before. So we could be thinking of things like functions as metric spaces rather than full-on spaces as that carry a lot of the properties that we end up using. For this section and for what we're doing this week, we're just going to be working in R to the n. These are normed spaces and have a lot of the qualities that we have, except for the quality of one vector may not be less than or greater than another vector. So we have to be careful about that. So now let's take this notion of distance and use it to our advantage here in Rm. Notice the slight generalization of this definition here, this being a sequence x sub n converging to a vector A in Rm. So this is, instead of real numbers, these are vectors. We'll say that these vectors converge if for every epsilon greater than 0, there is a cutoff point such that the value of the distance between the vectors x sub n minus the vector A is less than epsilon whenever the value of n is greater than or equal to this cutoff point. Now, this is a type of proof that I usually see students struggle with. This may not be the case for you, but when I am presenting students with this, even if they have seen epsilon-delta proofs before, this is usually the place in which we want to take a little bit of time. And that's exactly what this week is for. Let's take this week and really nail down epsilon-delta proofs to make sure that we have everything concrete. So let's first talk about how we can conceptualize epsilon-delta proofs before we move on. Let's think of it as a game between you and me, the professor, me, and you, the student. So let's play a game. I'm going to give you an epsilon that's greater than 0, and you're going to respond with a value n that's in the natural numbers. This is a game that we're playing. I start and give you a value that is positive, and you respond by giving me a natural number. Now there's the game. That's all we have to do for the game. We've been given the sequence. We've been given a limit, a limiting value for this, and we're now going back and forth with an epsilon value and an n. Now you're going to win this game if whenever the value of n is bigger than the value of n that you chose, the value of the absolute value or the norm, the distance between x of n and the vector a, is less than the value that I chose for epsilon. Otherwise, I'm going to win. So if you were unable to come up with a value of n that made this work, I'm going to win instead. Now, there's a notion of winning and losing in different cases, right? Because you could have just chosen the wrong value of n. You'd be like, hold up, let me rewind and see if this n is better. If you have a winning strategy, meaning regardless of the epsilon that I choose, you have a value of n that makes this work, then the sequence is going to converge. If you do not have a winning strategy, if instead I have a winning strategy, if I can give you an epsilon that makes no value of n that you could choose work, then the sequence is not going to converge. I recommend thinking about this analogy a little bit because putting it into the form of a game does trigger a few things in your head that's a little different than just thinking of it in terms of all F's, like quantifiers and negations. So I really like this method, and I want to encourage you to think about how this sort of game might be played. We'll try it here. Let's take two sequences x sub n and y sub n and r sub r to the m converging to a and b respectively. Then let's see if we can prove that the sequence x sub n plus y sub n converges to the vector a plus b. Notice that we want to show that this does hold, that this is true. So this means you need to have a winning strategy in this game. Here's how I kind of visualize this in my head. I've drawn the picture of how I am visualizing this. There are things that we have to start with in this game, which is that the sequence x sub n converges to A, the sequence y sub n converges to B. Now, I don't know about you, but sometimes it is very helpful for me to start putting down what these terms mean. And here, I'll go and try and make use of these quantifiers. Notice these quantifier uses that I'm using here. The upside down A is a for all quantifier. This says for all, if I'm saying it in English. For all epsilon greater than 0, this backwards E is going to be there exists a value of capital N inside the natural numbers. Here, this backwards is inside of symbol is short for such that. And you can see that my next thing is inside of parentheses because I am saying that this next thing in parentheses needs to be a true statement, this being an implication. It needs to always be true that whenever n is greater than or equal to the capital N, that implies that the distance between the vectors x sub n and a needs to be less than epsilon. So that's this statement that we get on the left. And on the right, I get the same statement, but just with y sub n and b in place of x sub n and a. All these little boxes are explaining what the definitions of the terms mean from the boxes that come above it. I usually want to do this first, because when I look at x sub n converges to a, I don't see much that I can manipulate mathematically. I want to be able to see that in front of me. So whenever I'm doing this in front of my students, I say, let's draw this box. What does this mean? Converges to A. And this usually is like, oh, now I see the connections between what I have to do and where I have to end up. It's because here I'm doing the same thing. For my ending sequence, I'm kind of working backwards a bit, saying that the sequence x sub n plus y sub n converges to the vector A plus B. And I'm going through and substituting that into the definition as well. So this is a strategy plan for us. There is a what we have, which is the stuff on the left, and what we want, which is the stuff on the right. And I encourage using this sort of tabular format whenever you're trying to build your proofs. Just kind of think of it as part of the scratch work. We know x sub n converges to A, so now you can say for any epsilon that you can plug in, you get an n value back from that definition of convergence. So notice that everything in the start column here since x sub n converges to a, for example, you get to choose the value of epsilon. However, the n value that comes out of it is not something that you can control. You just know that one exists. I see this sometimes within my students. They say, oh, I want my n to be n over, I want my n to be 10. And that's not necessarily true if we just know that the sequence x sub n converges to a. We know we have finished our proof once we're able to say the statement in the bottom of the end column. So that's where our game will begin. You have the tools in the start column to help you, and I'm going to give you an epsilon greater than 0 to start the process off in the end column. What are you going to do with that epsilon? So here's a hint to kind of get us started. That epsilon I gave you can now be used in the definitions in the start column because you get to choose what that epsilon is. I've given you an epsilon to start the game. If we successfully say this last sentence here in this box, then we win the game. And that's our goal, is to say whatever is inside of this box successfully. You get to choose what values of epsilon are given in the bottom left corner. It's just that the values of n that you get out from it, you can't control. We can thread the epsilon that is given to us, that I just gave to you in that beginning of saying the end column sentence, through both definitions in the bottom left corner to get values of, let's call them n1 and n2, so that whenever n is greater or equal to n1, the distance between x sub n and a is less than epsilon, and then whenever I have n greater or equal to n2, that the distance between y sub n and b needs to be less than epsilon. So we can use and harness the power of the epsilon that is given to us, or that I gave to you in this game, in order for you to get values of n that work neatly with it. But there's a couple of issues here. One is I have two values of n1 and n2. Well, that one is fixed a little bit pretty neatly. We can just say, let's take a cutoff point that is bigger than n1 or n2. Or you can even just say, let's take a max of n1 type and n2. Notice now for any values of n greater than this big N that I have, that the distance between x sub n and a and the distance between y sub n and b are all less than epsilon. But the issue is this. If I continue through the proof on this, and I'll save you the time on it, if I continue through the proof on this, then I'm going to get something that is less than 2 epsilon rather than something that is less than epsilon, like I'm trying to show over here. Now, a lot of mathematicians are okay if you get to something that's less than 2 epsilon, but I want to challenge us a little bit into what we're actually doing, because just getting something to be less than 2 epsilon means we're kind of missing some of the point, which is you want to be able to duck beneath any particular given epsilon value. And so we get to control our values of n so that we can duck beneath that given epsilon value. Some of you may be used to this already, and if you end up getting to a proof where something's less than 2 epsilon, then you're doing okay. But it's good to go ahead and be very rigorous with this. So for the proofs that I'm going to do, and that I encourage you to do if this is something new to you, try and get your values to be less than epsilon wherever possible. Not epsilon squared, not epsilon over 2, not 2 epsilon. Try and make it less than epsilon. Actually, epsilon over 2 would be fine with it, wouldn't it? Because epsilon over 2 would be less than epsilon. So you could just say that as part of your proof. So here's what I mean. Let me show you an example of what this sort of proof might look like. Let's fix epsilon greater than 0. That's the one that I gave you to start off. You now have to come up with a value of capital N. This is your cutoff point. Well, x sub n converges to a, so there's going to exist some n sub 1, so that whenever n is greater or equal to n sub 1, the distance between x sub n and a is less than, note the difference here, epsilon over 2. We're going to do the same thing for y sub n minus b and get that norm to be less than epsilon over 2 as well for past some cutoff point n sub 2. Then we're going to use that trick that we saw of making the cutoff point be the greater of the two values, n1 and n2. Then we go ahead and start breaking up the expression that's given to us in the bottom right corner of this box. We want to show that this is less than epsilon. So we're going to start manipulating this mathematical expression. We'll group some of the terms that go together, like x sub n and a should go together, y sub n and b should go together. So let's see that happen. X sub n minus a, y sub n minus b. Now I'm going to use the triangle inequality to say, okay, this is x and this is y, less than or equal to the norm of x plus the norm of y. Once I go through that, I see that that's the triangle inequality. And because of what I did up in the previous steps, each of these distances is less than epsilon over 2. and these add up together to be epsilon. So you can see a little bit of maybe a backwards approach that I wanted to take. Maybe in my scratch work, the way that I was starting this was I was taking something like x sub n plus y sub m and looking at minus a plus b and saying, can I get this mathematical expression to look similar to things that I know are true? So something I can do here is to take x sub n minus a and y sub n minus b and try and get them together like this. Now, to get this to be less than epsilon, I have to do a little bit of work. I know that I can control how small these things are, but how did I know that I could get them less than epsilon over 2? Because remember, for anything in that start column, you get to choose what that epsilon value is. I've given you a value, epsilon, to go and work with. But you can plug in whatever you would like to fill in the spot of epsilon in that bottom left column. Well, let's follow the path. So let's follow the path of epsilon more closely. I gave you an epsilon greater than 0. You got to choose what to plug in for epsilon in the definitions in the start column 2 slides before. The only requirement is that your choice for whatever goes into that slot be greater than 0. Well, epsilon over 2 is greater than 0, so you're good to go. You can choose any value here as long as this value is greater than 0. Regardless of the epsilon I gave you, epsilon over 2 is greater than 0. Notice you couldn't have said epsilon minus 1, for example, because the epsilon value I could have given you might have been 1/2, in which case you would have gone to something that was not greater than 0. But epsilon over 2 is fine, because it is something that is still greater than 0. So it's a good choice, and the rest of the definition will follow through, substituting in epsilon over 2 wherever we see epsilon. That's exactly why we were able to say that the distance between x sub n and a is less than epsilon over 2. And that got us to our epsilon there. I want us to practice with this, even if you're used to seeing it end up with 2 epsilon and someone telling you that that's fine, because I want our ending statement to be very convincing, which is that it mirrors the definition of what's happening. Again, if you were familiar with this concept and you know you get something less than 2 epsilon and it works, then that's fine. But for those of us who are just getting back into this, I want us to make sure that we're getting things that are less than epsilon. Let's practice one more time. Let's show that if the vectors x sub n converge to the vector a, then let's show that m times x sub n converges to m times a. Now we can go through and write out what this is in terms of our start and our end column. We're going to have, starting with, for all epsilon greater than 0, there exists a cutoff point n such that whenever n is greater than or equal to n, that's going to imply that the absolute, or the distance from x sub n to a is less than epsilon. So this is our start column. Our end column is going to be, well, I want to say the same thing for convergence, but I want it to now be with respect to the sequences m x sub n going to m sub a. So let's see if we can make something like that happen. Here's m x sub n minus m sub a. I want that to be less than epsilon. So maybe now I go through and do my scratch work. My scratch work says I want to, before I start the proof, try and figure out what I need my little values of epsilon to be in the start column. So I go to absolute value of mxn minus ma, and I start trying to make this look like x sub n minus a, which is something that I know I can control. Well, this is going to be equal to, if I take a look at this, I see that I can use a property of the real numbers, which is that if I take the distance between two vectors and they're both multiplied by a constant, I can take that distance out as long as I'm taking an absolute value around that scalar that I'm multiplying by. And then I'm left with x sub n and a's distance right inside of here. So if I would like for this to be less than epsilon, then really what I'm hoping for is to get x sub n minus a to be less than epsilon over the absolute value of the value of m. But I run into an issue here. Notice that I'm trying to figure out what this absolute value of x sub n minus a is, and I'm dividing by the absolute value of m to do that, but it is very possible that my value of m is 0. Now that's an issue, because I cannot divide by the absolute value of m if m is 0. The absolute value of that value would be 0 as well. So I need to kind of consider that as a separate case if I'm going to go through and do this proof. So let me go ahead and start my proof like that. I have to do a proof by cases. This is where I have to break up different parts of a proof to be able to deal with all possible scenarios that could happen. So in order for us to use this, I need my m to be not equal to 0. So I'm going to start with a case where m is equal to 0, because I actually think if m is equal to 0, I can handle this. If m equals 0, then mxn is equal to ma is equal to 0, the vector 0, for all values of n. And then we can just note that a sequence of 0 vectors and we can say, if we want to, a constant sequence, if we would like. Constant sequence of 0 vectors converges to 0. So we've got our case of m equals 0. Didn't need to think too much about this, just needed to note that and then kind of move on. If m is not equal to 0, now I can start going through and saying this sort of start-end process. And here's how we're going to go through and do it. We're going to say, kind of mirroring our previous proof, let's fix epsilon greater than 0. Then there exists a value, and we'll call it capital N, being in the natural numbers, such that the absolute value of x of n minus the vector a is less than epsilon over the absolute value of m. I need to check now that I've written this statement to make sure that it's justified. It is justified because I am given that x of n converges to a. So I can say for any positive value that there exists a cutoff point so that the distance between x of n and a grows to be as small as my value. The value I've chosen based on my work here is epsilon over the absolute value of m. Then, given this, we should be able to say that the absolute value of mxn minus the value of ma is going to be equal to, and we can kind of now just go through the motions a little bit, which is go back through our scratch work and write this sort of stuff that we wrote before, which kind of comes later in the proof. That is going to be a bit of a pattern, that this is less than absolute value of m times epsilon over the absolute value of m, and that this is equal to epsilon. So by definition, and I'll use sometimes DEFN for abbreviating, but I can go ahead and spell it out here. By definition, the sequence of vectors m x of n converges to the vector ma. All right. So this gives us our proof. Notice that there was a little bit of a start-end action going on and then some scratch work that took place before I got to the thing that I actually put on my piece of paper to turn in. My proof is going to say, here are the different cases that I worked with, and then eventually start tying in my scratch work, usually near the end, to say this is the kind of the reason behind everything that I've done to work through this. So my recommendation to you is to find problems similar to this, if this is something not quite familiar, and start working through it a little by little. We'll have some homework problems to help out with this, of course, but go through and practice this a lot. Again, we want this to be our bread and butter. We don't want to have to be dealing with the epsilon and deltas and stuff like that. We want that to be something very comfortable for us so that when we move on to the next steps, we're not juggling the new concepts together with these proofs that we're not quite too comfortable with. The game proceeds slightly differently, this game between Professor and me and Professor and you, when looking at the definition of a function f being continuous at a point a. Here, let's start with the real numbers for the sake of continuity. We'll get to a point where we're talking about continuity in terms of Rn as well. But let's start with the function going from R to R. We'll say that a function f from the real numbers to the real numbers is continuous at a point a in the real numbers if for all epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus f of a is less than epsilon. Before getting through the game, I want to go ahead and draw a picture because I'm a big fan of pictures. So let me go ahead and do that. So maybe I'm trying to say that this function that I've drawn is continuous at a point a, like right over here. So what I am attempting to say is this: given an epsilon window, so here from here, we're saying that this distance right here is epsilon, but there is in existence a delta window around this point, so this distance right here is a distance of delta, so that whenever I look at points inside of this window, if x minus a is x is delta close to a, then the y values are also epsilon close. Any x value that I choose inside of this green window should have its y values be inside of this purple window. This is essentially what I'm trying to say. The values of the function inside of the x window should fit entirely inside the y window. The window of y values is what we're attempting to say for this. So here's how the game is going to be played. I'm still going to give you an epsilon greater than 0, but now you are responding with a value of delta rather than a value of n. The difference here is slight but meaningful. The n that we were giving was a cutoff point for an infinite sequence, a sequence that went off to infinity. But instead of giving a cutoff point and looking at an infinitely going off value, we're now looking to say we're going to do a cutoff in a very small window and make a small window of values what is pertinent rather than something going off toward infinity. That's the difference between our nomenclature. Is that the capital N is meant to denote some sort of cutoff point in a sequence, whereas delta, like epsilon, is meant to denote a small number. You win if, whenever x is delta close to a, f of x is epsilon close to f of a. Otherwise, I win. If you have a winning strategy, the function is continuous at a. If I have a winning strategy, the function is not continuous at a. Now, I've gone through and given you some examples of things that do work in terms of our sequences from before, but let's see something in which I win. So this is a game that I, of course, have to love. Let's take the function, piecewise function, f of x equals 1 if x is greater than or equal to 0, and 2 if x is less than 0. Is this function continuous at x equals 0? Well, intuitively, we have a notion of continuity that comes to us from somewhere in the world, maybe grade school, somewhere else, which says this. If I have a piecewise function, I need to look to see if I need to pick up my pencil going from left to right. If I ever have to pick up my pencil going and drawing this function, and since I have to do it right here, then I should be able to say, okay, intuitively, this is not a continuous function. But how does this tell me that I am going to lose this game if I am playing against the professor? What is my way of making this work? There's some sort of jump at x equals 0 that I need to take advantage of. So that means that this shouldn't be continuous. So the professor has a winning strategy. So what epsilon could I choose, that is me, the professor, so that you have no choice of delta that wins you the game? There's got to be a winning strategy for me. I need to be able to choose an epsilon so that no matter what delta that you choose, I'm still going to win. Epsilon equals 1 ends up being good enough here. Let's talk about why. Notice by the definition, I need to be able to give you a choice to find delta greater than 0 so that whenever x is in between negative delta and delta, that's what we're doing when we're saying that the absolute value of x minus 0 is less than delta, is that we're just inside that little delta window. Then f of x minus 0, f of 0, which, by the way, I know f of 0 is equal to 1. That the value between the distance between f of x and 1 is less than epsilon. Now we can start seeing where things start going wrong in our picture. This delta window that you choose can be as narrow as you want it to be. But no matter how narrow you make it, there's still going to be some room here to the left of x equals 0. And that room to the left of x equals 0 is exactly what we're going to exploit. Because we don't really have any issues when x is greater than 0, but for any value of x less than 0, we see the value of the function f of x, which is what we'd be plugging in for f of x here in the expression, is equal to 2. So for any value delta greater than 0, anything here with, oops, I should have flipped this, should have written instead, negative delta is less than x is less than 0, that this implies that the distance between f of x and f of 0 is the distance between 2 minus 1. And that is not less than 1. So that fails our definition of continuity. Again, I'm hoping that this is not something that comes across as pedantic in any way. I just want it to be very clear so that we have the most solid understanding of these proofs as we move forward, because this is something that is going to be our bread and butter. We're going to see this all the time, and we're going to see it in a lot of different contexts. So having this really be instilled within us as something that we can handle, we can take on, is extremely pertinent to our success. We're now well equipped to break apart some proofs of these propositions. The function f, going from real numbers to real numbers, is continuous at a point A if and only if this latter part is sometimes called the sequential definition of continuity. This is sometimes called the sequential definition of continuity. Another definition of continuity, and I know it's a definition because of this if and only if part right here. And that's exactly what it means. If and only ifs are definitions. If the thing on the left is just a term and the thing on the right is something else, then that means we could have just defined continuity in this way. So this is the sequential definition of continuity. And we know that the other definitions of continuity are useful to us because they offer a different perspective. We will sometimes say, okay, let's let a function be continuous. Sometimes we'll use epsilon delta. Sometimes we will use sequences. So having access to all of these perspectives for the same term is just, we cannot proceed without all of these different perspectives. So first, let's make sure that this is a solid perception, that we can get this different way of formalizing the notion of continuity. So let's go through the proof. Remember, so this is a little bit of shorthand that I don't think I've used yet. For an if and only if proof, some other way to write this is sometimes written like this. See if that shows up well on the screen. It does. This bolded left and right arrow is a biconditional. That means that the thing on the left implies the thing on the right. The thing on the right implies the thing on the left. So both directions work. If you have something that's true on the left, that works on the right by modus ponens. You know how that sort of thing goes. Then the right on the right implies the left. So if you have the right, therefore you have the thing on the left. That's the other direction using modus ponens. So there's technically two things to prove. One of which is the fact that the left statement implies the right statement. That's what's meant by this arrow here, is that I am going and assuming something is true from the left and attempting to formalize the thing to be true on the right, just given the fact that the left side is true. So let's see that in this context. First, we suppose that f is continuous at x equals a. In this case, we are saying this is the epsilon delta definition. This is not with sequences there. Well, now I want to say that whenever you have a sequence x sub n converging to a, the limit of f of x sub n is f of a. So I need to start by getting that sequence. So here is me constructing a sequence x sub n. I'm saying let's take x sub n to be a sequence so that the limit of x sub n is equal to this value a. This is me setting up this right-hand side. I'm playing a game with you, the professor. The professor is giving me a sequence x sub n that converges to a. I now need to show that the limit of f of x sub n is f of a. Well, we're going to use the fact that x sub n converges to a. Let's say that for all epsilon greater than 0, there exists a delta greater than 0, so that f of x minus f of a is less than epsilon whenever the absolute value of x minus a is less than delta. Well, x sub n is going to converge to a. So what happens if I plug in x sub n here? Well, as long as I get x sub n minus a being less than delta, then that means, well, my value of x minus f of a is small enough to be within epsilon. So can I always get this to be the case? I absolutely can. I of course can, because in fact, I can do it by just saying x sub n converges to a. What does that mean? That there exists a cutoff point for that sequence so that for any value past that cutoff point, the distance between x sub n and a is less than delta. So notice that I'm kind of doing the definition of subsequence convergence here, and I'm using delta in place of my epsilon. And that's because that's exactly how I want to utilize that, since I see x sub n minus a somewhere else present in what's useful in this definition of continuity. So for any value of n greater than or equal to big N, I'm going to get that the distance between f of x sub n minus f of a is less than epsilon. We look at this last part of the sentence and notice that that is exactly the definition of the sequence f of x sub n converging to f of a. So that's exactly what we want. That's what we desire. So my recommendation is, if that was a little bit fast for you, try spelling it out. Try looking through, making the tables of everything that we did, of what we started with and what we ended with, and see what we did to get to that point. What were the missing pieces? And think about how this sort of proof worked. On the other hand, now let's go the opposite direction. This shorthand means that we are going from the right statement and saying that that implies the left statement. But an equivalent way to do this is to use the contrapositive. Remember that the contrapositive of this, if let's say I call the right statement R and the left statement L, then this is the same thing as trying to say something like this. Not L implies not R. So sometimes you will see this direction, but instead of me trying to prove that the left is true, given that the right is true, I will start with saying, suppose that f is not continuous at x equals a. And then I will try and prove that the right-hand side is not true as well. And that gives me the other side of this biconditional by the contrapositive. So let's start by saying f is not continuous at x equals a. Hence, as in our previous examples where we had to go through and think about how that means I, the professor, win the game, we are saying that there is some epsilon greater than 0 so that no matter what delta you choose, there is some x value where the distance between x minus a is less than delta, but the absolute value of f of x minus f of a is greater than or equal to epsilon. Now I need to negate this statement over here. Think about what that means. I need to say that this is not true. So what I need to do is form a negation. Some way that helps me to form a negation of a statement is to start by looking at the statement itself. Sometimes what I'll do is I'll try and convert the statement into quantifiers. Quantifiers being like that upside down a and backwards e. So for this, the way that you could write this statement in terms of quantifiers is like this. For all sequences x sub n converging to a, f of x sub n converges to f of a. That's what we want to say this statement, this one that we have outlined over here. So if I want to show that this statement is not true, then I need to go through and form its negation. The negation of a statement is going to be, one neat way to do it, if you've got it in terms of quantifiers, is to flip all of the quantifiers to be the opposite quantifier. For all becomes there exists a sequence. Notice here I'll also make some small changes to the English here, just to kind of help make sense of what's going on. There exists a sequence, x sub n converging to a. The comma above becomes a such that below. And then at the final part of the statement, I will say that f of x sub n does not converge to f of a. So I would like to now, in order to finish this part, find a sequence x sub n that converges to a so that f of x sub n does not converge to f of a. The picture here is, you're saying, given our picture from before, let's say this is the function that was 1 down here and 2 up here, and you're going to try and pick a function or a sequence that, although the x values of that sequence converge to the value x equals 0, the y values don't do the same thing. For example, you might have picked a sequence of values that just approach from the left-hand side. But you note here that we do have to be careful because there are some sequences that do converge to the y value as the x values converge to a. So we have to be a little bit careful in that definition. So as we go through and proceed through this, notice what we're using to try and find this sequence. Here's what we're going to do. We're going to use the fact that this function is not continuous, and we've gone through and negated the definition of continuity. Well, fix this epsilon. We're going to start there. Fix this epsilon, the one that says for all delta greater than 0, there is some x that makes the definition of continuity fail. And let's pick a sequence of deltas. Now, this should be true for all delta greater than 0. So if I pick delta sub n equal to 1 over n, well, then that's going to mean I'm always still able to find this x. I'll call that choice of x for some delta sub n. I'll make that choice x sub n. Let x sub n be the point guaranteed by the negation of the continuity definition given above. Well, x sub n is going to satisfy this, so x sub n minus a is going to be less than 1 over n. Notice that this means that x sub n converges to a. Because, well, x sub n is going to be less than this other sequence that converges to 0, so x sub n must converge to a. However, f of x sub n is always epsilon away from the value of f of a, regardless of my choice of n, and that was something that was guaranteed by this part of the definition in the negating continuity. So f of x sub n does not converge to f of a. That's the negation of the sequential definition of a limits that we gave right over here. We found the sequence x sub n that converges to a, so that f of x sub n does not converge to f of a. And so we are done. A similar definition of this continuity for a function holds whenever we're looking at r to the n going to r to the m. An analogous form of this proposition holds for multiple dimension functions, and we won't give the whole formulation or proof of that here, but it's very similar to what we would be doing here in this proposition. So notice that each of these proofs, sometimes I'm going to go through these slides and not give as much attention to proofs as I'm doing right now. Some of you are like, John, come on, get it on, right? Some of you are like, I'm soaking in all of this because I want to see where all of this stuff is coming from and kind of connect all of these pieces together. And that's exactly what I'm doing this for. In the future, we're not going to be able to go through proofs at this level of detail, picking apart. So having the tools yourself to pick these proofs apart is important. And make sure that you are using things like the homework help to be discussing this, using things like what we're going to be using for our reading to work with this, using your peers as well as myself to be helping out with each of these different components and these different parts. Do not be afraid to ask questions. We are not all perfect here. And let me be the one that is guiding us. But even I am not perfect, and you'll see that several times in this class. But at the end of the day, we're all going to be guiding one another in a special way. We're all going to be helping each other. I get to be a main guide, but we're all guiding each other. We're all being guided. Y'all are helping me as well to know how to best help you. And that's what we're doing here in this class. So what have we done so far? We've looked at the sequences and their convergence, continuity for functions. These are all big deals for us, and we're going to be seeing these pop around every now and then. I want to finish this up by looking at one more thing here when it comes to continuity, which is sometimes these definitions and these theorems involve multiple parts, and the proofs that we use will sometimes hide all of the scratch work that goes behind them. Let's see that here in this proposition. Let's assume that g is a function from the reals to the reals that is continuous at a point A, such that g of a is not equal to 0. The reason for that being not equal to 0 is immediate in this next sentence. If we define the function h of x to be 1 over g of x, then that function is continuous at A. Note here that if g of a is 0, then h of a is actually not defined. So we couldn't say it's continuous. So we're making the assumption here that g of a is not 0. That was necessary for us to make this definition of h of x being 1 over g of x and even talk about this at A. But we're going to use that fact a good bit in what is to come, so we'll keep that part in mind. Before getting into the proof, let's start the scratch work. Our goal is to make the value of 1 over g of x minus 1 over g of a small. These are our values of h of x and h of a, respectively, whenever the absolute value between x and minus a is smaller than delta. Okay, but notice that whenever that is smaller than delta, we're automatically going to have the absolute value of g of x minus g of a is less than epsilon. So that is something that we get to use to help us out. Let's start by rewriting our expression a little bit. This is what we want to make small, so I'm going to go ahead and do a little mathematical manipulation before I continue. I'm going to get a common denominator between these two fractions and split up the absolute value between numerator and different factors in the denominator. Should give me something that looks like this. Well, that didn't take long because now that we know g of a minus g of x is small, and it's an absolute value, we can say this fraction is small, right? Well, it's a little bit more complicated than that for two reasons. One, g of a might be very close to 0. And so that might be something that we need to be considering. Well, even then, it seems like you could just make g of x minus g of a smaller, right? Well, okay, sure. But what about g of x? If x is approaching a and g of a is very small, g of x might stay arbitrarily close to 0. So there's something there that we need to be careful about. We need to at least be able to control how big the fraction can be, which is correlating to how small the denominator can be. So we cannot allow, first of all, g of x to be equal to 0 at any time. That's not going to work because otherwise our function is not even defined in that delta neighborhood. So we need to be shrinking our delta to be past a point where g of x is equal to 0. Well, are we able to do that? Remember, our only tool right now is the fact that g is continuous at A. So is there a way that we can do this? Well, gratefully, there is a way. Here's an exercise for you, and I'll give a little picture to help us out. Let's say that this is our point that we're very close to here at 0 at. This is coming away from it. So let's say that this is g of a, or a comma g of a. Then, if we ask for the distance between g of x and g of a to be less than the absolute value of g of a, and notice, by the way, this is something we can control based on the fact that we get to choose the epsilon that is given to us in the definition of g being continuous at A. So because we can make this value small, we can actually guarantee the absolute value of g of x is greater than 0. So here is our picture. If the distance between g of x and g of a is less than the distance, or less than the absolute value of g of a, then the absolute value of g of x has to be greater than 0. Think about it this way. That value of the absolute value of g of a is the distance between that value and 0. So where can g of x be? It can only be anywhere inside of this window. It can't go lower than that point. It could also go a little bit higher, but that's no problem here because you get something that's positive. You can also draw a similar picture here if g of a happens to be negative, and that's important to us in this picture as well. Here, the absolute value is this value, and so our little window that is less than the absolute value of g of a looks something like this. Notice that each of these values and absolute value are greater than 0. There's another issue here, though, too, which is that what if the factor of absolute value g of x in the denominator gets close to 0? Well, then our function is going to blow up or approach an infinite value. That's not going to do well for keeping our expression small, so we want to make sure that in the proof that we're doing, we're rigorous enough to stay not only away from 0, but for anywhere close to 0 as well. So let's tighten our choice of epsilon just a little bit. What if instead of less than absolute value g of a, we just basically cut our window here in half? So let's say that I make this blue window over here. Say I cut this window in half. Well, then now not only are our values of g of x not equal to 0, they're also away from 0 by some sort of predetermined margin, given by whatever the absolute value of g of a is. Same thing in this picture. So I'm making these less than g of a over 2. Then in a similar way, we must have the absolute value of g of x is greater than the absolute value of g of a over 2. That's going to allow us to write this following proof. Let's assume that g is from the reals to reals continuous at the point A, so that g of a is not equal to 0. This is what we're starting from. Then the function h of x equals 1 over g of x is continuous at A. Let's see if we can do it. In order to show something is continuous, we've got to do an epsilon-delta argument, or we need to do a sequential definition of continuity. Either one would be fine. This one we're going to do using the epsilon-delta definition. So let's fix it epsilon greater than 0. Well, since g is continuous, there exists starting with a delta 1 greater than 0, such that the absolute value g of a minus g of x is less than, this is going to guarantee that our g of x is away from 0, whenever the absolute value of x minus a is less than delta 1. Let's go ahead and take our scratch work and start working with it a little bit here and see what we end up with. Now that we're at this point, remember, we want this value to be small if we can make it. So the way that we can, only way, however, that we can control these values is by using less than, so that we get eventually something that is less than epsilon. Well, we know that the absolute value of g of x, from our work from before, that the absolute value of g of x is greater than the absolute value of g of a over 2, from our work done on the previous slide. Well, that's in the denominator, so anything in the denominator is going to flip the sign if I make that substitution. So this is going to be less than, take a look at what we have here now. The denominator has replaced absolute value of g of x with the fraction absolute value of g of a over 2. Rewriting this a little bit, I get some sort of constant with respect to x times something that I know I can control and make small. And that's exactly what we're going to do in this next part. Notice this is a constant with respect to the value x, which is the only thing that I'm allowing to be inside of this little delta neighborhood. The a here is a fixed point. It's an arbitrary point, but it's fixed for the purposes of our proposition. So the only thing I need to do is make sure that I ask for this absolute value of g of x minus g of a to be less than the absolute value of g of a quantity squared over 2 times the value of epsilon that was given to me at the beginning of the proof. Now, this is okay for us to do. A, again, is a fixed point. Here's something that is not okay. If I had asked for the absolute value of g of a minus g of x to be less than absolute value of g of x, absolute value of g of a epsilon, then this would not have been okay. Because the thing on the right-hand side is not a fixed constant with respect to the thing that's being allowed to run in this delta neighborhood. This absolute value of g of x can change over time. Whatever this needs to be in terms of using the definition of continuity of g effectively needs to be some sort of constant. Needs to be a constant with respect to whatever is running. In this case, that's with respect to x. With respect to x. So this would not work This is not an appropriate use of a constant here. But this one, on the other hand, does work, because notice that this one does not reference x anywhere in the constant. It only references a, and that is something that is fixed in the proposition. This can be given whenever absolute value of x minus a is less than delta 2. So whenever absolute value of x minus a is less than the minimum of these two values, then we get, from the work we've already done, the absolute value, 1 over g of x minus 1 over g of a, is less than this value, which comes from right what's over here. And then we use this final less than to get everything to cancel and get equal, something that is equal to epsilon, as we desire. Some of our proofs will be this complicated, and some of them will incorporate more ideas than this. So this is the level of comfort I want us to be at. It's something that we can get to understanding these proofs when they come up, as well as writing these proofs whenever they become necessary. So what have we done? We've talked about sequential definitions for continuity, as well as epsilon-delta definitions for continuity, all of those relating back to sequences in terms of vectors, which connects the notions of norm and distance to those in more general contexts. Eventually, we'll be applying all of these in a very general context, which is known as the metric space. But that'll do it for me today. Thank you so much. Have a wonderful day.